Okay, so in this video we're going to talk about the intermediate value theorem. So what we're going to do is state what the theorem is, talk about why it might be true, and then see what happens if we drop this condition of continuity. So f of x has to be continuous, so we'll see what happens if we don't have that condition. And then we'll talk about a special case of this theorem that's more commonly used in calculus and things like that. So basically, this theorem says if f of x is continuous on a to b, then f of x attains every value between f of a and f of b on this interval from a to b. Okay, so that might sound kind of confusing, might sound like a mouthful. The fact is there are a lot of different ways to state this theorem, but it's really just a bunch of different ways of saying the same thing. And all it really says is that if you move continuously from one value to another, you hit every value in between, is basically what it says. So let's see a picture. If we draw a picture of that, it's probably going to be easier to understand. And giving like a real formal proof of this requires some advanced math, not really too crazy, but a little bit beyond the scope of calculus. So the best we can do right now is build up some intuition with pictures and things like that. So let's say we have this function y equals f of x, and we'll put a here, and we'll put b here. Okay, so this right here is going to be b comma f of b, and this right here is a comma f of a. Okay, so f of a is going to be this y value right here, and f of b, if we move on over to the left like that, is going to be right here. F of b is right here. Okay? So what do we see? What's happening with this function? What's it doing? So this function is continuous, right? It's continuous on this interval from a to b, and it looks like it's continuous outside, but we don't care what's happening outside of the interval. We only care about what's happening inside this interval from a to b. Okay, so between x equals a and x equals b is all we care about here. Okay? So we just need the function to be continuous on that interval. So the intermediate value theorem tells us, since we have this continuity on this interval, then the intermediate value theorem tells us that f of x will attain every value between f of a and f of b on this interval from a to b. So in other words, if you give me any number between f of a and f of b, I'm going to give you back a number between a and b such that f of my number equals your number. So in other words, you give me some value between f of a and f of b, I'm going to give you a c between a and b such that f of c equals that value that you're looking for. Okay? So, and again, to say that another way, or to say it more, a shorter way, if you move continuously from f of a to f of b, you're going to hit every value in between, because you're moving continuously. So it's really, really, really important to have that continuity there, because if you're not moving continuously, anything could happen. You might hit every value in between, you might not. Okay, so you got to be really careful with that. But the point is, if you move continuously from one value to another, you're going to hit every value in between each of those values, in between those two values. Okay? So, for example, if you were to say, all right, I want a value of x such that f of x equals this y coordinate right here. Okay? Well, all I have to do is move on over to the right, and the intermediate value theorem guarantees that I'm going to find an x between a and b, and here it is, such that f of that x equals that value that you want. Okay? So, and in this case, we found only one here. So, but what if you wanted a value of x that gives you this y coordinate right here? Well, we come over to the right, and we see one right here. We can keep going, we see another one. Keep going, we see yet another one. Okay, so in this case, there's actually three of them. Okay, so this x value here, this x value here, and this x value here. Okay. Now, we can't know that just in general from the intermediate value theorem, because the intermediate value theorem doesn't tell us how many there are, it just tells us that there is at least one such x. Okay, so it tells us that if f of x is continuous on this interval from a to b, then for every value of the function between f of a and f of b, there is at least one x value such that f of x equals whatever value you're looking for between these two guys. Okay. So the intermediate value theorem is an example of what's called an existence theorem, because it just tells you that something exists. It doesn't tell you how to find it. It doesn't tell you, what it is. It just tells you that it exists and that at least one of them exists. So it's called an existence theorem for that reason, because it just tells you something exists and not how to find it or what it is. So again, just can't say this enough, really. It's very important. If you move continuously from one value to another, then you're going to hit every value in between. Okay? So notice the way we drew this, f of a is smaller than f of b, but absolutely nothing that we said used that fact. So we could just as easily have a different kind of picture where f of b is smaller than f of a, and it would all be exactly the same. As long as the function is continuous, the exact same principle would apply. Okay? So since absolutely nothing we said used the fact that f of a is less than f of b, it could be the other way around and everything would be fine. But let's see what happens if we drop that continuity condition. So remember, the very important thing here is that f of x is continuous, because if you move continuously between two values, then you have to hit every value in between. If you don't move continuously between two values, anything can happen. Well, there's really only two possibilities. You hit every value in between or you don't. So let's see some examples of that. Okay, so x-axis, y-axis. So let's see what happens if we have a function kind of sort of something like this. And then let's put a hole right here and then go back down like this. Okay. So let's put A right here, and we'll put B, let's put B right here. Okay. So this is going to be, oh, also this function here, I probably should finish, probably complete it here. This is y equals f of x. Okay. So this right here is the point A comma f of a. And this right here is the point B, comma, f of b. Okay, so what do we have right here? We have this hole, and we have this kind of like jump discontinuity here, right? So we have this jump discontinuity, and that's going to be bad, so that means we can't use the intermediate value theorem. So what's going to happen? Well, here, so let's come on over to our y-axis. So here's f of a, and then here, if we move on over here, this is going to be f of b right here. Okay, here's f of b. So, since this function is not continuous, so then we can't use the intermediate value theorem. And as it turns out, let's say, what if we wanted to find a value of x between a and b such that f of x equals this y-coordinate? Well, we're not going to find one, because what happens if we try to find this y-coordinate on the graph between a and b? Well, first of all, there's one right here, right? But that's not between a and b, so that totally doesn't count. We don't care what's happening to the left of a, we don't care what's happening to the right of b, just totally forget about all that. All we care about is what's happening between a and b. Well, if we try to find this y-coordinate between a and b, we're not gonna, right? We're just gonna keep going beyond b, and we're just not gonna hit it there. So between a and b here, we do not have this y-coordinate because this function jumps. Okay, this function is discontinuous, so we do not have this guarantee that this value of x exists between a and b, such that f of x equals that y-coordinate we want. So this is an example of what could go wrong if the function is discontinuous. Okay? Now I want to point out that just because the function is discontinuous does not mean you're not going to find the value you're looking for, right? So this is an example of a function being discontinuous, and there is no such x value that gives us f of x equals that coordinate we want. Okay? Now it could just as easily be the other way, or it could happen the other way, that we still have a discontinuous function, but maybe we still can find any value we want. So let's draw a picture of that. And I just want to emphasize that because, you know, I don't want people to think that, oh, well, if f of x is continuous and then on this interval from a to b, then f of x attains every value between f of a and f of b. Well, then if f of x is not continuous, then it's not going to attain every value. Well, you can't necessarily say that. That's not necessarily true. If f of x is not continuous, you might attain every value or you might not. You just can't say for sure. So we just saw an example where f of x is not continuous and we do not attain every value. So let's see an example where f of x is not continuous but we still do attain every value. So we'll do something like this again. But now let's do this. So we'll open this up this way. Okay, so this is going to be y equals f of x. Let's put let me extend this a little bit actually. Sorry about that. I have to extend this over here. Okay, so we're going to put A right here, and we're going to put B over here. Okay. So this right here is A comma f of A. Okay, so yeah, A is negative in this case, but that means absolutely nothing. A could be negative, B could be positive, they could both be negative, they could both be positive, it does not matter at all. So this right here is f of A. And then B corresponds to about this point right here, so that's B comma f of B. Okay. And then that corresponds to this y-coordinate right here, f of B. Okay. So notice this function is not continuous on this interval from A to B. So this function is not continuously moving from f of A to f of B. Okay, so here's f of A right here, here's f of B right here. This function does not continuously move from f of A to f of B. But if we want to find, but notice, you know, if you look at this picture here, you see that this function still has every value between f of A and f of B. Even though the function is not continuous, it still attains every value between them. So let's say, what if we wanted this y-coordinate right here? Well, if we just move on over to the graph, we see here's an x between A and B that gives that to us. What if we want this y-coordinate right here? Move on over to the graph. Here's an x really close to B, but still less than B, that gives us that y-coordinate. Okay? What if we want this y value right here? Okay? Well, if we move over to the right, we're not going to find one, we're just going to hit that open circle. But if we move to the left, we see here's one, just slightly bigger than A. Okay? So we're still going to find an x value here. Okay? So my point here is that for any value between f of A and f of B, we can find an x between A and B such that f of x equals that value we want. So in other words, even though this function does not continuously move from f of A to f of B, we can still find, or it still attains every value in between that. So my point again is that if f of x is not continuous on this interval, then f of x might attain every value between f of A and f of B, or it might not. Okay, so this right here is an example of a function being not continuous, but still attaining every value. And just before this, we saw an example of a function that's not continuous and did not attain every value. So my point is that, again, I just can't stress this enough. If f of x is not continuous, you cannot conclude anything. So if you apply the intermediate value theorem, your only two conclusions are going to be, yes, we do attain every value in between, or I don't know. Your conclusion is never, no, we don't attain every value. Your conclusion is either we do attain every value, or I don't know. Okay? So that's just sort of an explanation of what can happen if you drop the continuity condition. So that's the intermediate value theorem in general. So now let's talk about this special case here, where it's more commonly used in calculus and things like that. So a special case, if f of x is continuous on an interval from A to B, and if f of A and f of B have opposite signs, then there is a c in this interval from A to B such that f of c equals 0. Okay? So how's that a special case of the intermediate value theorem? It sounds, actually almost sounds more complicated. And it just sounds more complicated because there's more to say. But really, the only thing it's saying, let's just draw a picture. So what does it mean for f of A and f of B to have opposite signs? It means one of them is positive and one of them is negative. Does not matter which one's which. Either one could be positive and the other one be negative. It does not matter at all. X-axis, y-axis. So let's actually, since we're talking about negative and positive y-coordinates, let's move our x-axis up a little bit. So here's our x-axis, here's our y-axis. All right, so let's say we have a function doing something like that. So let's go ahead and put A right here, and we'll put B over here. Okay, so here's A and here's B. So here is f of A, right? Here's A comma f of A. And here is B comma f of B. Oh, and I forgot to label the function, but the function is y equals f of x. Okay. So notice f of A is positive, right? F of A is above the x-axis, so it's positive. F of B is below the x-axis, so it's negative. So we see that because this function f of x is continuous, okay, it's continuously moving from positive value to a negative value, it's going to hit 0 somewhere in between, right? So really, this is a special case of the intermediate value theorem, because the intermediate value theorem says if you move continuously from one value to another, you hit every value in between. Well, in particular, if you move continuously from positive to negative, you're going to hit 0, right? So if you continuously move from one value to another, you hit everywhere in between, every value in between. So if you continuously move from positive to negative, you're going to have to cross 0 somewhere. Okay? And this is really the more useful special case or version of the intermediate value theorem, because it tells you that a 0 of the function exists on some interval. So this tells you that there's some number c such that f of c equals 0, and that's a root or a 0 of the function, right? So that's useful for that. And we'll do a couple examples in the upcoming videos of using the intermediate value theorem, the special case. Okay? So there are some things worth pointing out here, though. So first of all, f of x has to be continuous. We already saw what could go wrong if f of x is not continuous. Okay, so over here we saw some pictures of that, saw what could go wrong if f of x is not continuous. The same exact thing applies to the special case. Okay, if f of x is not continuous, you might have this number c or you might not. Okay, it's the exact same thing. You just might have that, you might not. You cannot conclude anything. But also what's kind of dangerous is if f of a and f of b have the same sign, then we can't conclude anything for the special case. So if f of a and f of b are both positive, or if they're both negative, then there might be this number c or there might not. So let's see some examples of that. So first of all, I just want to point out that f of a is positive here and f of b is negative, and we do cross 0 here. But just because this does not rely on the fact that f of a is the positive one. So it could just as easily have been f of a is negative and f of b is positive, and it would still be the exact same thing. The point is, as long as you move from a positive value to a negative value continuously, as long as you continuously move from positive to negative, you're going to cross 0 somewhere. Or if you continuously move from negative to positive, then you're going to cross 0 somewhere. Okay, so that's the point. So now let's play around with this. Let's see what happens if f of a and f of b have the same sign. Okay, so if they're both positive or if they're both negative. So we'll see some examples of that real quick. So just 2 more quick examples, that'll be it for this video. And then we'll do some actual calculations and stuff like that in the upcoming videos. So let's draw, I guess, the same kind of function, why not? So y equals f of x. Okay, so let's put a right here, and we'll put b over here. Okay, so notice f of a, let's actually move b over a little bit because it looks like they're about the same thing. That doesn't really matter, but I don't want to keep things too simple here. Let's put b right here. Okay, so here's f of a, and then here's f of b over here. Okay, so f of a and f of b, they're both positive, right? They're both positive, and notice in between a and b, there is no number. Okay, there's no c. We don't have the c value such that f of c is 0. Now again, I just want to point out, just because f of a and f of b have the same sign, that does not automatically mean that this c does not exist. It just means we cannot say for sure. So here's an example of f of a and f of b both having the same sign, but there is no c in between them such that f of c is 0. Okay? Well, what if we use a different b? So we'll keep the same a, but what if we use a different b? What if, so we'll forget about this b. Let's maybe use this b right here. Okay. So what if we use that b? Well, then what do we see? So f of a and f of b, they're still both positive, right? They're still both positive. F of a and f of b both have the same sign, but here we actually see that there is some point where the function crosses the x-axis. So there is the number c such that f of c is 0. And actually here's another one, right? So here's two values of x such that f of x is 0. So we do have this number c, right? So again, my point is that if you don't have these conditions here, then you just cannot conclude anything. So if f of x is continuous on this interval, and if f of a and f of b have opposite signs, then you are guaranteed there is at least one c. You don't know how many there are, you don't know where they are. Well, you know they're in the interval at least, but you don't know how to find them. So again, this is just an existence theorem. But as long as you have these conditions being true, then you're guaranteed that at least one c exists in this interval, such that f of c is 0. If the function is not continuous, you cannot conclude anything. You might have the c, you might not. If f of a and f of b don't have opposite signs, if they have the same sign, you can't conclude anything. You might have the c, you might not. So we just saw 2 quick examples of what happens if f of a and f of b have the same sign. Okay, so when we had b over here, there was no c in between them that was a 0. Now that we have b over here, there's actually 2 c's in between them, such that f of c is 0. Okay? So again, the very important takeaway point here is that when you use this intermediate value theorem, or the special case here, when you use the special case, your conclusion is either, yes, there is the C, or I don't know, there might be a C. Okay, so we'll see some examples in the upcoming videos.